All right, guys, what I want to do right now is, first of all, start by reviewing a little bit of the material that we've covered with respect to Newton's second laws and Newton's second law. And really what I want to do is go over three different kinds of problems that we've been going over in class. Some of you maybe are pretty confident or pretty solid with these problems, but my sense is that most of you actually are not entirely comfortable yet with these Newton's second law problems. So I want to go over a few of them so that you'll have this on video. And for some of you, just seeing these problems, watching these videos over and over again might be one of the ways you can master this material. At the end of the video, after I've gone over these three problems, then I'm going to introduce a little bit of new information that we're going to work on in class tomorrow. So a few sample problems and then some new info. So let's start with some of our sample problems. So to remember, what we're dealing with here is Newton's second law, which says that the acceleration of an object is equal to the net force over the mass. So I'm saying A equals F over M. And we've had a lot of practice problems with this. The first type of practice problem that I want to revisit is the case of free fall. This is a special case of the, oh, I'm sorry, I don't want to do free fall, my bad. I want to do, let's do this here. Bear with me, sorry. My eraser's not working all that well at the moment. There we go, that's slightly better. I want to talk about, start over here, I want to talk about terminal velocity. Okay, so we talked about this in class. If you remember, what terminal velocity is all about is this is the case where an object is falling, but it has reached a point where it falls at constant speed. And we went over this in some detail, right? We said that when an object is falling, as it speeds up, it encounters more and more and more air resistance. And as it does so, the net force decreases and the acceleration decreases. And in fact, you can reach a point where the net force is zero, the acceleration is zero, and so it falls with constant velocity. And I want to visit that case. So maybe we have a ball falling here. Here's this ball or rock, whatever it is. And it's falling, and let's say it's falling right now, and it has just begun to fall. So maybe I've just dropped it. And if I've just dropped it, what forces are acting? Well, we've got weight downwards. We call that mg. And since I just released it, it hasn't sped up at all, so there's no resistance force. There's no force acting upwards. Now let's say that the mass of this rock, let's say it's a 5 kilogram rock. Mass is 5 kilograms. Which means that mg is 5 times 9.8, which is going to be 49 newtons of force. So what's the acceleration of the rock? Well, according to Newton's second law, F over M, the only force acting is this 49 newtons. So the acceleration is just going to be 49 divided by 5 kilograms is equal to 9.8 meters per second squared. This is the free fall acceleration. And maybe it makes sense that this rock is in free fall acceleration right now because there's no air resistance yet. It hasn't sped up yet, so there's no air resistance. Make sure that you understand what I've done here. I went through this a little bit quickly, but we've done this before, so I'm going over it a bit quickly. This is the weight, the force of gravity acting on the rock. M, the mass, times G, 9.8. It's the only force acting, so my acceleration equation turns into 49 over 5. 49 is the force. This is the net force over the mass, which is 5, and I got an acceleration of 9.8. So now let's imagine some later point. Here's the rock at some later point, and now weight is still acting. Gravity is still pulling this rock down. It's still mg equals 49. There's no change there. Okay, gravity is still gravity. But now there is an upward force because it's falling now in air. So now there is an upward force, and I'm just going to tell you that this upward force, this resistance force R, I'm just going to arbitrarily decide at this point it's 20 newtons. There's a way to calculate air resistance. We're not going to go into it right now. Magically, I'm telling you it has a resistance force of 20 newtons. So now when we go to calculate the acceleration, the first thing I need to figure out is what's the net force. Well, the net force, F net, is going to be equal to this value, 49, minus the resistance force of 20. So I'm going to say the net force is 49 minus 20. Okay? Hopefully you're understanding where that's coming from. That's 29 newtons. Oh, by the way, I should have done this up here. As I mentioned in class, this is kind of your free choice, but I'm going to choose to call down the negative direction. So let's make that negative 29, which means that this should have been negative 49. Negative 49. This is negative 9.8. So that negative is kind of your free choice, right? But I'm going to choose, as I have done, I'm going to choose here to call down. This is the negative direction. So make all those down vectors negative. So this is now the net force. I take the 49 minus the 20, and it's 29 down, so I make it negative. All right, well, what's the acceleration now? The acceleration is negative 29. That's my net force over my mass, which is 5. And that's going to give me, what is that like? That's going to be something like, what is that going to be, about 5.8 meters per second squared? Negative 5.8 meters per second squared. So we can see what's happened. Well, look at the acceleration. The acceleration here was 9.8, negative 9.8, and now it's negative 5.8. Okay, so it has changed. The acceleration value has changed, and that's because air resistance here has become a factor. As the rock sped up, the air resistance increased. As the air resistance increased, the net force decreased. As the net force decreases, the acceleration decreases. This is Newton's second law in action. All right, well, now we're at a point where the rock has sped up further, and now I'm going to say we're at this point here. That's terrible rock. Here's the rock. And now the net force has increased, or not, the resistance force has increased so that it's equal to the weight. So here's mg, still 49. And now I'm going to say that the resistance force, R, is also 49. Well, what's the net force now? Well, now it's 0. 49 minus 49 is 0 newtons. There's no net force. These are equal and opposite. They cancel out. So the net force is 0. So when I go to calculate my acceleration, I say 0 is the net force divided by 5. And of course, that's just 0 meters per second squared. Okay? So now the acceleration is 0. What does that mean? That means the velocity is not changing. This means right here, this means constant velocity. Okay, constant velocity. This is what we call terminal velocity. Okay, this rock will now fall at constant speed. It will no longer speed up. I know we went over that in some detail in class, but I wanted to revisit it because I know it was giving some folks difficulty. Okay. So I mentioned 3 practice problems. That was one of them. The next one I want to do is one that we were doing in class recently, which is this really classic case where we had a, this is a real classic Newton's law, second law problem here. We had the table. This is a table. For right now, we're going to assume that this table is frictionless. Later in the video, we're going to consider friction. So this will look familiar. We have this frictionless table, and on the frictionless table, we have a block. Here is this block. And I'm going to decide right now that this is a 10 kilogram block. And this 10 kilogram block is on a frictionless table, and it's connected by a rope, goes over a pulley, and it's connected to another block, which has a mass of 5 kilograms. And now the question I put to you, like we did in class, was what's the acceleration? Of the 10 kilogram block. Okay, that's the question. This is what we're going to try to determine here. What is the acceleration of that 10 kilogram block? So let's think this through a little bit. if we can, let's think about the forces that are acting here. Let's start with a 5 kilogram block. We know that there is a force here downwards, mg. Okay, that mg, that's 5 times 9.8 equals 49 newtons. Okay, this force is acting on the system. Okay, now let's keep in mind, we said this in class, you can treat this whole thing as one object, right? That's what I'm going to do. I'm going to treat this thing as one object. You've got 10 kilograms here, 5 kilograms here, but they're connected by a rope, so I'm going to treat them as a single object. And the reason that the whole system is going to accelerate is because of this force. This force is accelerating the system. In fact, this is the only force that I'm interested in this problem. We know that there's a force here, mg, that's going to be 98 newtons. I just did 10 times 9.8. But that force is canceled out by the normal force. There's this force here, normal force, which is also going to be 98 newtons. These are equal and opposite. They cancel out, and so they're irrelevant. They don't play any role in this problem. And they don't play any role in this problem, like I said, because there is no friction, right? You could have friction in here. We're going to deal a little bit later on with what happens if there's a friction force and friction between the block and the table. But for right now, we're ignoring friction. So the only force that's acting is this 49 Newton force. That's the only force that's at play here. So if I want to know the acceleration of this block, well, bear in mind that the entire system has to accelerate. So when I go to calculate the acceleration, I say the acceleration is the net force, 49 newtons, right? This is my net force. That is the net force, because there's no other force acting against it. Divided by the mass. Well, you might be tempted to say that the mass is only 10, but remember, this 10 kilogram mass is not the whole system. The whole system is the 10 and the 5 put together. In other words, the whole mass is the 15 kilograms, 10 plus 5. So if I calculate this out, I get 3 1/3 meters per second squared. That right there is the acceleration of the whole system, and therefore the acceleration of the 10 kilogram block. Okay, so there's two things to realize there, two details. First of all, make sure you understand why the net force is 49. Why this here is the only force that matters in this problem. Make sure that you get that. If you don't, let me know in class and I can try to clarify. Also, make sure you understand why I'm dividing by 15. Why didn't I divide by 10? Because the whole system has to accelerate. And the whole system includes both masses. 10 plus 5 is 15 kilograms. So, we've done some problems like this. You did a lab involving this kind of calculation. I just want to make sure that it makes sense to you. Alright, third practice problem that I want to do is a little bit new. We haven't done this, but I want to do it now, which is what if I had those same blocks, the 10 and the 5, but now what I want to imagine is that they're hanging from a pulley. Both of them are connected to a pulley. So here's a pulley, and I've got a 5 kilogram block here, that's 5 kilograms, and then I've got a 10 kilogram block here, 10 kilogram. So this is 5 kilograms and 10 kilograms. Maybe I should try to put in the kg in there, kilograms. And now I want to know, okay, now the question is, what's the acceleration? Okay. Well, now, how many forces do I have to worry about? Just one? No, I have to worry about two, because you've got this force here, mg, 5 times 9.8 equals 49 newtons. And you've got this force here. This is also in play now, right? This is in play because this 10 kilogram block is not on a table. Right here, in the previous problem, we ignored this 98 Newton force because the block was on a table. It was supported. It was being held up. But now, that's not the case anymore. In this problem here, that is not the case. So this mg, 10 times 9.8 equals 98 newtons. That is no longer canceled out. This is now a relevant force. So, okay, I have to go calculate the acceleration now. acceleration is net force over mass. Well, what's the net force? The net force is 98 minus 49. What's the mass? Well, it's both blocks that have to get accelerated, so I'm going to add their masses, 15. I subtracted these two. That might be a little bit confusing to you because it looks like these arrows are pointed in the same direction. It looks like they're both down, but keep in mind that they're oppositional, right? They're opposing one another. The 5 kilogram block is trying to pull up on the 10 kilogram block. The 10 kilogram block is trying to pull up on the 5 kilogram block. These two forces are in opposition. They're against one another. Make sure you get that. So I subtracted them. I added the mass, of course, because I have to consider the mass of the whole system, which is 10 plus 5 or 15. So I calculate this out. This is 53 over 15. And that's going to be what is that, like 3.5, 3.5-ish meters per second squared. And that's my final answer. Okay. Again, make sure you understand how I got this net force here, why I did this, why I subtracted those, and make sure you understand why that's 15. Did problems, we haven't done one exactly like this in class, but it's essentially the same reasoning as before. So hopefully those practice problems, those 3 sample problems, have helped you understand Newton's third law, or Newton's second law. We're going to do more work with Newton's second law in class, so be prepared for that. Okay, well, I promised you a little bit of new information, and here it is. I want to get into some new stuff now. And I've hinted, and we've talked a little bit about friction. And now I want to get into friction in more detail. What is friction? How do you calculate it? Well, we talked about friction. This is a force that resists motion. It opposes motion. Okay, so for right now, let's say it's a force between surfaces, okay, and it resists motion. So, for instance, if I had a surface here, let's say that I've got this tabletop, I don't know what this is, some sort of a table, and I've got a block on top of this table. No matter how smooth these surfaces are, if you looked on a microscopic level at this point, at this area right here, this contact point, you'd see, if you looked at it really, really closely, that the bottom of the block is bumpy. And the top of the table is also bumpy. And so as these surfaces try to move past one another, right, the block maybe is trying to go that way, or the surface is trying to go that way. As they try to move past one another, these little bumps are going to hit one another, right? They're going to grind together. And as they do, that grinding is going to oppose the sliding of these two surfaces past one another. And we call this force friction. So maybe in this problem, maybe you're pulling right this way. Maybe there's a pulling force this way. Now let me give that a color. So maybe you're pulling the block this way with some force P. And now what I'm saying to you is that there's a frictional force backwards here, friction. In the previous problem we didn't have friction, but now we're going to imagine that there is some frictional force here. And I want to know, how would we figure out what is the friction? How do we calculate the frictional force? Can we come up with an equation to calculate friction, so the force of friction? And it turns out you can. If these surfaces are sliding past one another, you can calculate it, and it's not that hard. There's only 2 things that matter. The first thing that matters is how bumpy, how rough these surfaces are. All right, so if this is, if this is really, really smooth block and a really smooth table, the friction is going to be relatively minimal, right? Imagine this is ice. If this is ice on ice, that's going to be very little bumping and grinding between those surfaces. If, however, these are rough surfaces, maybe if it's sandpaper on wood, there's going to be a lot more friction. So the first thing that matters is the roughness of the surface, and the way we account for the roughness of the surface is by a value called mu. This mu here, this is called the coefficient of friction. Okay, so it's the Greek letter mu, and it stands for the coefficient of friction. Now this is a constant. How do you know what it is? Well, you look it up, and you can find online or in a textbook, if you go to the appendix, you can find the mu values for any two surfaces, right? If it was, sandpaper on wood, that would be a mu value. You could look up mu value for steel on wood, sandpaper on glass, ice on steel, whatever. You could look up these various mu values, and they're going to vary. The larger the mu value, the rougher the surfaces. The smaller the mu value, the smoother the surfaces. Okay, so that's the first thing. And this is, again, let me just write that this is a measure of roughness of the two surfaces. All right, well, what else matters? Well, there's another thing that's important, and that's how hard are these surfaces pressed together. In other words, if this block is really heavy, you can imagine that the force between the surfaces is very, very big. If it's not heavy, then the force between the surfaces is small. And it might be obvious to you just sort of intuitively that would matter, but the reason is, let's look at this picture right here. If these surfaces are being pressed together hard, all these little bumps are going to get caught on one another a lot more. If the surfaces aren't being forced together very hard, then these bumps aren't going to get caught on each other quite so much. So the other thing that matters is how hard the surfaces are in contact with one another. And, well, how do we account for that? Well, one way to think about it is that it's going to be equal to the normal force, right? So if this is the weight of the block down, the normal force is the contact force between them, right? This is the normal force. Right, there are these other two forces. So one way to think about the force between the surfaces is to think about it as the normal force. So F normal. And there you go. That's our equation for friction now. Only two things that matter. The roughness of the surface as determined by the mu value, and then the contact force between them, the normal force. In this case, the normal force here would be equal to the weight mg in this particular instance. All right. Normal force, contact force between the two surfaces, mu, a measurement of how rough the surfaces are. So let's try to put this in practice if we can. And actually, maybe I'll actually just use this picture if I can. I'm going to go ahead and try and erase that right there, and I'll do a little calculation. Let's imagine, I'm just going to tell you, let's imagine that this block is in equilibrium. Maybe it's moving at constant velocity, maybe it's at rest. We don't know, we don't care. All we know is that it's in equilibrium. That's all that really matters to us. It might be worth remembering that based on this picture, as I said many times before, you cannot tell based on this force diagram if this thing is moving or if it's at rest. All you can tell is that it's not accelerating, right? All these forces cancel out, so it's not accelerating. All right, well, let's see. I'm going to determine, I'm just going to say that the mass of this thing, let's say that the mass of this block is 3 kilograms. So let's say it has a mass of 3 kilograms. I'm going to do black. M is 3 kilograms, and let's say the pushing force P here is 15 newtons. So you're pulling or pushing, whatever you're doing, with a force of 15 newtons, and this thing is in equilibrium, and its mass is 3 kilograms. And now what I'm going to ask you is, what's the mu value between these two surfaces? Can we calculate this thing? Can we calculate mu for this particular case? All right, well, how the hell would I begin with this? Well, first of all, let's realize that if the pushing force P is 15 newtons, then the friction force must also be 15 newtons, right? The force of friction must also be 15 newtons. Because, as I said, this is in equilibrium, right? These forces right here and right here are equal. So if the P is 15, the friction is 15. So that means if I use my friction equation, I can say 15 equals mu times the normal force. Okay, well, what's the normal force? Well, here it is. That's the normal force, but what is it? Well, it's, in this case, has to be equal to mg, right? This block is not accelerating in the y direction, up and down, obviously. So these two must be equal, so it must be equal to mg. Well, what's mg? Well, mg is 3 times 9.8, which is 29.4 newtons. So now I can say 15 equals mu times 29.4, which means, give myself a little more room here, mu equals 15 divided by 29.4, which is going to be very roughly 0.5. So mu is 0.5. This is the mu value. A word on this, there are no units for mu. Mu is dimensionless. All it is a constant. And you can see why. This is measured in newtons and this is measured in newtons, so the newtons cancel and you have no dimension. So this is one case, if I ask you to solve for mu, you do not need to put units on it because there are no units. No units. Hopefully that made sense. Again, friction and the pulling force, or P, these are equal because the thing's in equilibrium. The normal force has to be equal to the weight, so the normal force is this value here, 29.4. That is the normal force here. Hopefully that makes sense to you. And now this is a measurement of the mu value. All right, so that's an introduction to friction plus some more practice problems, Newton's second law. We're going to continue practicing Newton's second law in next class, and in particular we're going to talk about friction in Newton's second law, and then after that we will get into the third law. We haven't talked about the third law yet, but that's coming, so something to look forward to for next time.